Let's dive into radiation and radioactive decay. By understanding radiation and radioactive decay, it really builds your picture, builds your knowledge of an atom, especially the nucleus of the atom and how it acts. Now let's go back to isotopes. If you watched the earlier video that talked about the structure of the atom, we went over ions, went over isotopes. We're going to focus in on isotopes. And if you didn't watch that, there'll be a link down there popping up somewhere. You can watch that. Here's my reminder. That let's say I have an atom of carbon. All right, here's my example atom. That atom will always have 6 protons if it's carbon, because carbon always has 6 protons. But the thing is, I could find atoms all over the place and they might not have 6 neutrons. In other words, the number of neutrons in carbon can vary and it's still carbon. But if the number of neutrons vary, it's called an isotope. And that's where we start our conversation about radioactive decay. Now, this was in an earlier lesson, but I want to make sure that you understand where we're at with this. So if you need to fast forward, fast forward. If you don't, then follow along. Let me show you what an isotope is. We're going to count up the number of protons. And in this one right here, we have 6 protons. They have a positive charge. They also have a mass of 1 atomic mass unit, which we can abbreviate both of these ways down here. Neutrons also have a mass of 1. So here's a neutron, 1, 2, 3, 4, 5, 6. We have 6 neutrons. To find the mass, we add the protons. It's the mass of the nucleus. We add the protons plus the neutrons. We get a mass of 12. So this is carbon 12. Carbon with a mass of 12. This one over here has 1, 2, 3, 4, 5, 6 protons. And it has 1, 2, 3, 4, 5, 6, 7 neutrons. Now neutrons don't have a charge, so I'm not putting a charge with that. When I add those up, I get 13. So this is carbon with a mass of 13. We call it carbon 13. Now, I'm not saying carbon 13 exists a lot in nature. I'm just using this as an example. Over here, again, we have 6 protons. They have a positive charge. And we have 1, 2, 3, 4, 5, 6, 7, 8 neutrons. That's a total mass of 14. This is carbon 14. Now, this does exist in nature. We're going to carry this on as we learn about radiation and radioactive decay. These are all carbon, but they're isotopes of carbon. It's going to be useful to have a couple of key terms here. Radioactivity is one of them, and that's the emission of ionizing radiation or particles by the spontaneous disintegration of atomic nuclei. That's a lot. That's a lot to try to understand, but I'm going to teach you all of that right here as we go through the rest of this lesson. But we're going to use the example of radioactive carbon-14. 2 more key terms that you need to know is parent isotope. There are lots of radioactive elements, all right? And when they start off, the one that we're examining, we'll call that the parent isotope. We're going to use carbon-14 as our example. And then eventually, if it loses its radiation and becomes stable, that's called the daughter product. In our case, that's going to be nitrogen-14. Carbon-14 is going to end up as nitrogen-14, and then it's going to be perfectly happy and stable. Now, how is this even possible? Now, if radiation is when nuclei radiate particles and energy out of a nucleus, it's probably best to first understand why this happens, and then we can go over what it actually is. So why does radiation occur? I like to use the example because it's something that hopefully you can relate to, is that what if I went out and found your car? If you don't have a car, let's pretend you do. And I took the wheels off your car and I put square wheels on your car. When you come out and get in your car and start to drive along, what is it going to be like? This is going to be it's going to be a really bumpy ride. But let's say you drive enough and those square wheels, as you drive, chunks or pieces start to break off of them. Okay? Basically, what you're doing is, because there's so much jarring and vibrating that pieces of the wheels are breaking off. And as they do, if you drive enough, eventually those pieces will break off and you'll end up with more round wheels until finally they have sort of smoothed themselves out. And also, what happened to your ride? It used to be really unstable. It used to be really bumpy. It was really out of balance. But as you go along and as pieces break off or wear off the tires and they become nice and round and smooth again, you become stable. Well, this is a fair sort of analogy to what a nucleus is like. Okay? If an atom is stable, it means the forces in the nucleus, that are holding it together are balanced. But if it's unstable, if it's radioactive, it's like square wheels on your car, right? The forces that are holding the nucleus together are unstable. Let's say it's vibrating, kind of not very nice vibration. But if particles got jostled around and fly out of there, then maybe it's not vibrating quite as much. The ride becomes a little more smooth. This radiating of energy and particles and pieces out of an atom, just like the pieces and particles falling off your square tires to make them more smooth, that's called radiation. It's called radioactive decay. So that's why it happens, but let's get into what it actually is. There are three main types of radiation, right? We're going to really focus on those three main types, but just so you know, in my class in high school chemistry, we add two more because these two exist. They're not quite as common as the other three, but I think they're really important to at least know what they are because I like to tie everything we're learning into the real world. And this down here, especially this positron emission, there's some amazing things going on in science and in chemistry with positron emission. And I want you and I want my students to know about those. Now, I'm going to go through these, but what I will highly encourage you to do is write this stuff down. You're going to need it. And if you follow along in more lessons with me, you're going to literally need it all year long. So let's start off with alpha radiation. Alpha radiation are called alpha particles. Now, not all radiation are particles. Some radiation is just energy, but alpha is a particle. That particle consists of two protons and two neutrons. Now, protons have a positive charge, neutrons have a neutral charge. So if you have two protons and two neutrons stuck together, well, the whole thing has a positive charge. So here's what, if you could see it, this is what an alpha particle looks like. It's equivalent to a helium-4 nucleus because helium is number 2 on the periodic table. That means it has two protons. Well, look at this. It has two protons, right? And 4 means the mass. 1, 2, 3, 4. Now, this doesn't have any electrons around it. And this thing actually goes shooting out of the nucleus of an atom like a bullet, like a little teeny tiny subatomic bullet, which is what can make alpha particles dangerous. So we're going to write this way. This is useful because now if we can write it this way, we can do math with it. We can do nuclear reaction calculations. We write He because, well, that is essentially what it is, right? It has two protons and it has a mass of 4. So what does that mean? Oh, let me show you this. This is also the symbol that you'll oftentimes see for alpha particles. It is a lowercase Greek alpha. It kind of looks like the letter A. Kind of sounds like alphabet. Like in English, we get our alphabet, and the first letter is the A, which comes from the Greek alpha. There's a lot of connections here. And perhaps this is like the first form of radiation found, so the first letter of the alpha. Anyway, I'm going to show you how to write nuclear decay equations. When an atom gives off or radiates radioactive decay, we can show what the products are. We've got radium-226. The way I write that is Ra, because radium on the periodic table is Ra. I have it over here too, just in case. And if you remember from earlier lessons, we put the mass of the particle up here, which in this case is radium with a mass of 226. There are other radiums. There are still radiums, but they might have a different mass because they're isotopes of radium. Then I look up radium on the periodic table, and I see that radium has 88 protons. So I put the 88 down here. I put an arrow to show that this radium, 226, is going to undergo some sort of change. Something is happening to it. And I find out, well, when it changes, it actually breaks into two particles. One of those particles is radon-222. So I find, happy radon on my periodic table. It's right here. It is number 86. So I write down Rn for radon, Rn, and radon has an atomic number of 86, so I put that down here. And this particular radon is 222. 222. Now I'm going to show you a trick here, because this radium broke apart into two things. One of those things is radon 222. What's the other thing? And oftentimes, if you end up having to do calculations with this will not be provided for you. It'll say radium 226 decays and turns into radon 222. What radioactive particle did it release? Well, here's the thing. We have to have, I'm going to put a question mark here, and I'm going to put a question mark here, and I'm going to put a question mark here, because we're going to write it like this. Something plus 222 equals 226. What? Wait. 4 plus 222 is 226. Law of conservation of mass. If this thing broke up into two things, those two things together have to equal what you originally started with. So 226. 222 plus 4 was 226. Okay, well, let's look at the bottom part here. Something plus 86 equals 88. In other words, 88, if it breaks apart and one of those things has 86 protons, then what? Oh, well, let's go clear that out. And 2 plus 86 is 88. Now, this question mark here, we only have one particle so far, right? That's an alpha particle. And we know that it has, let's clear this out. We write He, which is an alpha particle. We could just write the symbol alpha here. So radium-226 undergoes radioactive decay, turns into radon-222 when it shoots an alpha particle out of its nucleus. Why does an alpha particle shoot out of its nucleus? Because it's unbalanced. It's like a square wheel trying to go down the road, and pieces are going to break off until it becomes balanced. So let's watch this. We've got radium-226, and if it undergoes radioactive decay, we know it's going to lose an alpha particle. It goes shooting out of the nucleus. And then the question becomes, well, what is it now? If it lost an alpha particle, what is it now? This is now radon-222. Radon is also radioactive. So now that radon might lose a chunk. It might give off radiation, turn into something new. That something new might also be, and it goes on and on and on. It's called the radioactive decay chain. The next one of the big three is beta radiation. And just like in my class, I don't need to really tell you anything about it if you truly understand what we've been covering. B, this is the symbol for beta. This 0 tells us the mass of that particle. So it has a mass of 0, has no mass, and it has a -1 here. Now, we've always said that's the number of protons, or the number of positive things. So if it's a -1, it's actually the opposite of a positive thing. A negative thing. What did we say were the negative things? This is an interesting thing. A beta particle is when a neutron, remember I said at the beginning that neutrons are actually made up of other things, and those other things sometimes can fall apart, and parts of it stay away. And so this is when a neutron loses the negative part, and the other parts stay behind. So if that's the case, and one of the neutrons loses its negative part, well, what's left? Because a neutron is made of negative and positive parts. The positive parts are left. What do we call a positive part in the nucleus? We call it a proton. So basically what happens is, watch this, a neutron, let's go back. A neutron loses its negative part, we call that a beta particle, and it turns into a proton. So a neutron can turn into a proton when it undergoes radioactive decay. Carbon-14, so we have carbon. This is carbon-14, so we'll put the 14 up there. And on my periodic table, carbon is number 6. It has 6 protons. This is showing that something happens to it. We know it's going to undergo radioactive decay because that's what we're learning about. And it turns into nitrogen-14. So we put nitrogen. This nitrogen has a mass of 14. And when I look it up, nitrogen is number 7 on the periodic table, which means there are 7 protons. Now, wait a minute. How can carbon turn into nitrogen? Well, let's finish out the problem. 14, well, that was the mass of it to begin with. So did the mass change? No. And over here, we have 6 protons, but over here we have 7 protons. The only way the math would work for this is to have a -1. -1 plus 7 is 6. This released a beta particle. Carbon-14 is radioactive. It's got like a square tire going down the road, and to become more stable, to become less bumpy, to become more, it loses a beta particle and it turns into nitrogen-14. The last of the big three is gamma radiation. Gamma radiation is different than the other twos because gamma radiation are gamma rays. It's high energy radiation that has no mass and has no charge. So if we think, how would we write that out? Well, this is the symbol we use. It has no mass, it has no charge, and this is the Greek lowercase gamma. So we use this symbol. Now, how then, if we go back to our example, how would I be able to calculate that a gamma? You wouldn't be able to calculate because it has no mass and it has no charge. So how in the world would I know that it also has gamma rays that are being released? Well, I need a detector to detect that. I don't have one with me. I don't even need one because this is telling me that 2 gamma rays are released, so I can just include them here to show that I have my overall equation correct, giving off both alpha particles and gamma radiation. So remember, the next two are not quite as common, but I do think they're important at least to understand and to know about. Neutron radiation means that a neutron is kicked out of the nucleus. Again, square wheel bouncing down the road. Only certain particles can fall off to make it more stable, to give it less vibration. And apparently sometimes a neutron can go shooting out of there. If it does, it's written this way, 1 over 0. I'm just going to put the whole equation up there and you can check it and we'll move on to the next one. 1 plus 12 is 13. 0 plus 4 is 4. So a neutron went shooting out of the nucleus, and that's neutron radiation. The last one is positron emission. A positron is a particle with a positive charge that has the same mass as an electron. So a positron is written this way. It has a mass of 0. Electrons have a mass of 0. It has a charge of 1. Electrons have a charge of -1. So we write it this way because essentially it's an electron, but it's an electron that's got an opposite charge. Well, in the quantum world, everything has an anti. Anti means opposite. So if there's such thing as an electron, which has no mass but has a charge of -1, there must also be something that has a mass of 0 but has a charge of +1. Well, that would be an anti-electron, which we call a positron. So look, if we're trying to do this mathematically, 38, it's still 38 over here, so that has to be a 0. 19, this is 18, that has to be a 1. Oh, this is a positron. Let's do a quick summary then. What's the symbol for an alpha particle? It is 42He. Sometimes you'll see it written as literally the Greek alpha symbol. The mass right here is 4. The charge is 2. I'm going to put a plus with it just to show that it's got a positive charge. Now the relative energy is, we're just going to compare these three. This one has the lowest of the three. So an alpha particle doesn't have a ton of energy. It's like a little bullet, a little subatomic bullet shooting, but doesn't carry a ton of energy. That'll be important in some later lessons. Beta particle, that was 0, -1e. And what's the mass? 0. What's the charge? -1 or 1 minus. This is medium, or compared to the other two, it's middle. This one, just so you know, is high, like really high energy. Gamma has no mass, has no charge, and has that symbol. No mass, no charge. It's just energy. This is a good way to kind of see how this whole thing works. If we start with uranium-238, that uranium-238 is radioactive. It's unstable. It's like a square wheel. Eventually, that uranium is going to give off an alpha particle. Look, there's our symbol. And turn into thorium-234, which will give off a beta particle, which the next product will give off a beta particle. And the next particle will give off an alpha particle, and an alpha particle, and an alpha. And it keeps giving off particles like that square wheel, and you're trying to drive down the road and chunks are falling off until finally, look, and there's lots of paths and different ways that this can give off radiation until you finally end up over here with stable lead-206. This takes a long time. I mean, Radioactive uranium, which turns into all these other things, can exist for a very, very long time. And every one of those is going to give off some energy. Let me show you a really cool application of this that you're probably quite familiar with, and it has to do with these smoke detectors. I want you to be able to see what's inside a smoke detector. That little teeny tiny spot right there in the middle is radioactive americium. That's one of the elements on the periodic table. It is a man-made radioactive element. And for a long time, science they didn't know, like, well, what would you use that for? Then somebody had a really clever solution, because radioactive americium is giving off alpha particles. Oh, we just learned about those. And alpha particles don't have a ton of energy, but it's going to give off a constant stream of alpha particles over time. Now, here's my disclaimer, do not do this. Like, don't do this at home. Don't take it apart. I did to show you this, and then I safely put it away, and I only get it out when we do this lesson with my students. Well, let me show you something. This right here detects radiation. There's a sensor up there, and every time a radioactive particle goes through the sensor, it beeps. So that means there's radiation all around us. Not a lot. Oh, maybe there is a lot here. But let me show you the difference between background radiation, what's just around us, and this radioactive americium that's in your smoke detector. Listen to this. Whoa, that's crazy. So your smoke detector is detecting this constant stream of alpha particles shooting through it. Now, let me just take something like a piece of paper. This is my periodic table that I've been using. I'm going to put that in between. Look at that. It basically stops because alpha particles don't have a lot of energy. So most of the alpha particles are not making it through the paper to the sensor. Now, why does that matter? Well, let's think about this. If this is a smoke detector, right, and smoke particles can get right in between that little teeny tiny, that tiny distance between them, and the smoke particles can soak up the alpha particles, just like this piece of paper does, then all of a sudden this goes beep, 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 and tells you, oh my gosh, something is blocking all those alpha particles from getting to my sensor. And if it's smoke particles, you need to get out of the house. And so this is a really, really creative solution of using something that we think of being very harmful and very destructive to save lives. And maybe, that's something that you'll do. As you learn more and more about chemistry, you'll give us the next advancements that we need to save more lives. I hope you do. I also hope that you keep on learning.